好，那开始啊。So okay, uh, so now I'll lead this paper reading. Today we're gonna discuss this paper, MeltPT, a pattern package for basaltic Hawai rock thermobarometric analysis with application to Hawaii. And this is this year's paper, new paper, and the author is Fergus McNab and Patrick Ball. So the first author, the first author is Fergus McNab, and he got his master degree at Oxford and a PhD degree at Cambridge, and he did a 1 year postdoc in Cambridge, and now he's worked for German Research Center for Geosciences, and as a postdoc, and the second author is Patrick Ball, which we discussed his paper last year, and I found that Fergus McNab and Patrick Ball they were classmates when they getting their master degree and PhD. And the research, Fergus McNab, he focused on the solid earth process, which are controlled by the magmatism and the tectonics. And he usually used some method like big data and geodynamics to solve this problem. So about the introduction of this paper, so it's important to understand the volcanic melting and how the melting behavior in the mantle. One way to understand that is to analyze the component of the basalt melt, because the melt have exchanged the elements with a solid phase under different temperature and pressure. So we can do the experiments to figure out the relationship between the uh, composition of the basaltic sample and the temperature and pressure. So we can use the composition to calculate the pressure and temperature. But the problem we have here is many people have introduced their different thermobarometers, but there's not uh, a standard framework to apply and compare in a self-confidence and reproduce way, because besides the traditional way, when we use it's complicated because we have to read their equations and do the calculation one step by one step in the Excel. But now they introduced their Python package called MeltPT. We can use Python to do the easier way to do it. And their Python package included three major functions. The first is estimate the original major elements component and calculate the equilibration, pressures, and temperature. And third is calculate melt fraction and mantle potential temperatures. So this is their documentary of their Python package. So they introduce their Python package functions in this website, and these include the installation and how their thermobarometers how could it be used, and some case studies in this paper. They show the detail here, and for the first part of their function, they use their Python package to estimate the primary melt composition. And for estimating primary composition, we have to estimate the volatile contents first. So such as the H2O and the carbon dioxide, when the melt come up to the surface, they will lose the volatile content. So we have to use other proxy to estimate the volatile contents. In their model, they use the CE to uh, calculate the H2O content for the primary melt. And for the second part is correcting for the fractionation. Because when the melt coming up and the first phase to crystallize is the olivine phase, so they have to add the olivine back to calculate the primary melt composition. And the target value of the FO value is they said is 90 because they found it in the like olivine phenocryst or xanthus. They think that that value is the primary melt composition value. And and the they set the partitional coefficient, uh, which is a KD at 0.3, and they calculate that we need to add the olivine at 40%. And if we set the partition coefficient at a varying function, we will need like 70%, 60% olivine addition. And when we add the olivine, the MgO concentration have been increased because the olivine have more MgO, and the other contents like FeO and silicon oxide, they remains constant, and other elements has been and diluted because the olivine didn't have much other elements. And so we got the first part of primary melt composition. Then the second part is to use the traditional thermobarometer to calculate the pressure and temperature of the melt. So they use this. They choose a sample from the Planck and Fossey 2016, and they use this all this thermobarometer to calculate the result. And they think when the partition coefficient they set to 0.3, the result close to the original result from the Planck and Fossey 2016. And they also use other thermobarometer and get the other results. They are different. So in the later research, they use this. They think the Planck and the Fossey thermobarometry is better for their research. And the third part, they estimate the melt fraction and the potential temperature. They use update model from the McNab 2018 paper, which is can be used to estimate the potential temperature and melt fraction. Basically, their idea is to fitting a line that fitting a melting path line close to their sample temperature and pressure estimating, and this grid line will get an intersection with the solidus. So and they also have the slope of adiabatic, so they can have this potential temperature. Basically, idea is this, and they can calculate the melt fraction from the distance between the sample point to the intersection. So they can get this 3.6 and 6.3. They are based on different depend on different partition coefficients. Um, and okay, and they got their pattern package. They use their pattern package for some application. The first application is they are trying to estimate the mantle potential temperature. So they get their data, their MOB data from Gale 2013, and they use the Planck-Fossey thermobarometer to calculate this mob status pressure and temperature, and they found that the result almost like between the 1 and 2 GPa and 1300 and 1500 degrees C. And they use these pressure and temperature data to calculate the potential temperature, which use the last step. And they found the result, all the data mean value is 1450 degrees C. And they found the potential temperature have a negative correlation with the Na 19% and the ridge depth. And that is according to the traditional research, previous research, and they think their result is their model is fit on this case study, and then they exclude some high temperature point because they think that high temperature point, which larger than 1450, they exclude that point because they think that point related to the plume, related to some higher temperature case. So they only use the data have lower temperature. So the potential temperature they calculated is 1402 degrees C. That's their result. And the second application is they applicate their model to Hawaii. So the Hawaii volcano chain has present from 5.8 million years to 1.2 million years. And there are two different geochemical different trend, which called Kia trend and Loy trend. They have different isotopic features, and there are three phases of the volcano. There are three different phases of the volcano. They are shelled phase and post-shell phase and rejuvenated phase. Oh, sorry, rejuvenated phase. And so there are three questions they conclude still not be solved, which are the mantle plume under the Hawaii, the temperature, the excess temperature of the mantle plume under the Hawaii volcanoes, and the mechanism of the rejuvenated phase, and the mechanism of these two, how these two trains how the two trains produce. And first, they collect the data. The data basically from the updated Patrick Ball 2021 paper, and there are almost 6,000 rows data, and only 700 have H2O contents, but there are 2,000 have the CE contents. So they use the CE contents and H2O CE ratio to calculate the H2O of the primary melt. So, like I said before, they have to calculate the primary melt composition to calculate the melt equilibration pressure and temperature. So they have to set up some value in their model. First is they think these three phases have three different source, uh, like geochemical source. So they set the average value of the H2O CE ratio as different from their data, and they set this value and they got the CE value, so they can calculate the H2O value. And they set this FO value at 90. So when they calculate the primary melt, they will use this value because their target uh, melting FO value is 90. And they also need this iron plus 3 iron total value to ratio to uh, estimate the primary melt. And for the post shell, they didn't have the data. You can see from this red corner figure, they didn't have the uh, red data, the post shell data, and they just use the shell data. And other data like rejuvenated phase, they use the mean uh, uh, iron plus 3 total iron ratio, and and therefore they can calculate their different place potential temperature. And they found that their results also according to the previous study, they lie within the result of previous study. And also the excess temperature is the plume temperature minus the mantle potential temperature. And they think the result uh, is right. And the second question of the Hawaii application is how the rejuvenated phase rejuvenated phase erupted, and they analyzed the geochemical of these three phases, and you can see from this figure that the blue points, which represent the rejuvenated phase, they have a higher NVER ratio, and also have a higher ND isotopic ratio, because so they are enriched phase. So they assume that the Hawaii volcano go through a change in the source composition, because they are obviously from the different geochemical source. And the third question is why is there are two different geochemical train, which are lower train and the Kia train. So the obvious difference is that the Kia train have the rejuvenated phase. So as I just said, the rejuvenated phase have uh, they are enriched of the isotopic, the ND isotopic value, and it's also a deep melting. You can see the blue melt is deeper, and the Kia train they think the Kia train uh the shell phase also higher than the lower train the shell phase. So they think the Kia train the shell phase is a mixture of the deeper and enriched melting. So and besides the rejuvenated only happened after the 3 million years, and in 3 million years there's plate motion change. So they think the plate motion change lead to the result of the Kia train. So there is a deeper melting happened and influence the geochemical features of the Kia train. Uh, okay, so this is a conclusion of this paper. They present an open source pattern package MeltPT for estimating the temperature and pressure, and also apply to a two case study, which is mantle potential temperature and Hawaii Island. And also the MeltPT is designed to uh, designed for the user to add any new methods and function. Yeah, that's all.